Here, what you see in front of you is the result of the substitution of the summation into our resultant wave function. The first term corresponds to the summation over the positive ends, and the second term corresponding to the negative ends, and C1 and C2 are their aforementioned constants. As we discussed before, the contribution from the poles, this one and this one, should result in their correct exponent in their asymptotic behavior, and it is supposed to yield their incoming incident plane wave. Right, so now we need to fix C1 and C2 constants. So how do we do this? Well, there are two requirements. The first one is that the wave function should be continuous for all values of t, and the second one, it should be single-valued. Right, so, but this integral can't be taken exactly, so we need to somehow to approximate it. So the best way to fix these constants is to compute the asymptotics of the wave function at large values of r. So let's do this. This is the requirement of the largeness of r. Now let's analyze the structure of the integrand. First thing you notice, there is an exponent here, f of t. And it's a standard Bessel type exponent, and it has saddles at point I, minus I, and I. And the steepest descent directions are actually pi by 4 and 3 pi by 4. And the contour should be placed in such a manner that it is gliding through the lowest regions of the real part of the exponent of this function. Right. However, the initial requirement is that the contour should pass in such a way that everywhere along the contour, the modulus of t should be greater than 1. So here is our unit circle. So everywhere, these are contour should be outside this unit circle. Right. However, there are also contributions from these two saddles. But there is also the contribution from the poles, which lead to their incident plane wave. So these two saddles yield 1 over square root of lambda, or square root of r in our particular case, dependence, which are responsible for their, we expect that they will give us their outgoing scattered wave. And the poles hopefully will give us the correct plane wave. Right, so let's sketch the approximate position of the poles. Well, first of all, let's recall that there are 4 quadrants in the complex plane. And if, both poles are positioned somewhere on a unit circle, somewhere here. If, however, these poles are positioned in their second and the third quadrant, then the contour can actually pass far from them and remain low on their real part of this exponent function. So basically these two poles won't contribute to the asymptotics of our wave function. Indeed, well, we can place the contour somewhere here, so they will pass far from these contours, so from these poles, so there will be no contribution. Actually, we could draw the exact. You could do this with Mathematica, and you will have to look it up, the appropriate code in their supplementary material. But their stationary phase line passing through, for example, saddle minus I looks as follows. And there is an adjacent line which passes through their second saddle, upper saddle. Right, so as you see, in principle, these two lines, they can go far from the poles if they are positioned here, and the poles won't give us the correct contribution. So let's actually figure out the approximate position of the poles itself. So suppose angle theta belongs to their range from 0 to pi. That means that theta minus pi by 2 belongs to the region from minus pi by 2, segment from minus pi by 2 to pi by 2. Now we understand that at least for such angles, there will always be a pole positioned either in the first or the fourth quadrant. But what will it mean? Well, suppose our pole is positioned somewhere here. But this is the steepest descent line on stationary phase line. But we can't deform the contour in such a way, we can't make a smooth deformation of the contour in such a way that it passes through along this steepest descent line. Because this deformation will have to cross the position of the pole. So instead, what is going to happen? That when we deform the contour will have to circle around this pole, and the correct deformation will include the contribution from the residue type contribution from this pole. Okay, let's actually draw the steepest descent direction line or stationary phase line, which passes through this pole. By stationary phase line, I mean, of course, the stationary phase line of the real part of the exponent function. You can draw again it with Wolfram Mathematica. If you do this, you will discover that this line has a slope here, which points directly to the origin, but otherwise it looks as follows. Right. So, and now we kind of see what would be the correct deformation of the contour. The contour should glide through this stationary phase line, like that. Then it has to go out of the origin in the steepest direction to the point corresponding to this pole, circle around the pole, return back. Again, this is steepest descent direction, and then leave the origin and go along the second steepest descent line to pass through their upper saddle. So quite exotic contour. Our function here, well, defined our multivalued function t to delta alpha is of course single value due to the presence of this branch cut. And as a result, the contributions from these two paths toward the pole and from the pole will cancel, and the resulting integral, the resulting contribution would be the combination of three terms. Two terms are the saddles, and the third term is the contribution from the pole, which is basically a residue type contribution. Right, so let's actually consider the other segment of the possible values of theta. Theta may belong to the region from minus pi to 0. That means that minus theta belongs to the region from 0 to pi, and minus theta minus pi by 2 belong to the region from, again, from minus pi by 2 to pi by 2. Right. So in case we have the angle belonging to the opposite range from minus pi to 0, then again there will be a pole in the complex plane which belong to either the first and fourth quadrant. So after the deformation, we'll have to attach this pole-like contribution to our asymptotics. And now let's actually compute these two asymptotics, these two pole-like contributions to our wave function for both ranges of the angle, for the first one here and for the second one here. So the first one. And so the contribution, of course, using Cauchy theorem, is just 2 pi I times the residue of our integrand. So 2 pi I cancel the 2 pi I here in the denominator. The exponent function, as we expect, will give us just the correct plane wave type expression. So the main exponent will be just e2 minus I k r cosine theta, the plane wave, plus, of course, I integer part of alpha times theta. Then there will be this t in the denominator, which should be substituted by this exponent e to I theta minus pi by 2, which, by the way, cancel this exponential. Next, this C1 constant, and T2 delta alpha. So it's e to I theta delta alpha minus I pi by 2 delta alpha. I remind you that delta alpha is the fractional part of their alpha parameter, where alpha is a magnetic flux. So it's alpha minus integer part of alpha. Right. So there is this factor is reduced to 1. And here is their principal asymptotic behavior representing their incident plane wave. But this for the region of thetas from 0 to pi. The second region, from minus pi to 0. And then we expect that this pole contribute to our integral. Because you can check yourself that this pole will lie outside this first and fourth quadrant of the complex plane. Right, so again, the principal exponent will be the same, e to minus ikr cosine theta plus I integer part of alpha theta. And then this contribution, this term, will give us, so t here and t in the denominator cancel. So we'll have C2 constant times T2 minus delta alpha. So we'll get I theta delta alpha plus I pi by 2 delta alpha. And I think that's more or less it, I think. And constant times constant C2. Well, actually, these two functions should represent the same wave function. We expect this. So these two formulas should be identical. And in fact, but they act, so they are valid in different regions of their our initial plane, of the scattering plane. So, but they should match at point theta equals 0. And if you compare them, you will notice they are almost identical. They have identical theta dependence. The only difference between them is that if in these two constants, and the difference between these constant factors, they are completely conjugate. Here you have I pi by 2 times delta alpha, and here you have the same exponent but with minus sign. So the condition of their continuity of our wave function looks like looks as follows. So C1 times e2 minus I pi by 2 delta alpha must simply be equal to C2 times e to I pi by 2 times delta alpha with plus sign. Right. So, and finally, if we require this, if we impose this condition, then these two functions will coincide. But what we want to get, so we actually want to fix even C1 constant, so both of them. So this fixation is achieved via the requirement that our plane wave function has a unit modulus. So we want it to have the appearance as, it should look like e to minus I kr cosine theta. And to achieve this, we actually say that C1 should be equal to e to I pi by 2 times delta alpha. After this, our incoming plane wave becomes a simple e to minus I kr cosine theta plus this theta dependence, and this delta alpha plus integer part of alpha gives us full alpha plus I alpha theta. The peculiar thing that you may notice is that alpha may be an arbitrary real number. And this function is problematic because it should coincide with itself for theta equal to 0 and to pi. But here it's just not true, because for due to the fact that this is not an integer number, we have so this factor becomes 1 for theta equal to 0 and e to 2 pi I alpha for theta equal to 2 pi. But these are two identical points. Does that mean that the magnetic field should be quantized? Because, as you remember, the alpha parameter is the ratio of the magnetic flux to the magnetic flux quantum. But of course, in the real experiment, the magnetic flux, the initial magnetic flux, is not quantized. So this alpha parameter should not be an integer. And somehow we'll have to resolve this paradox later. But right now, our next step is to make sure that there is no outgoing scattered waves in this expression, because we want our wave function to reflect the real physical process of the scattering event. So let's see how this is checked on our next slide.